And the next and final speaker is Guangcan Yang, Modulation and Control of DNA Charge Inversion.
Thanks, organizer, to having me here to present our recent work. So now a little bit late, maybe, you may be a little bit tired, but I try to speed up a little bit and end up so, okay. I would try to tell you about DNA charge inversion and condensation, how to control and modulation. So, I will try to talk about these things. First, I will demonstrate the how to control charge inversion of DNA, and then I will try to tell you about the hydrolyzed metal ions and its interaction with DNA. And then I'll tell you some specific monovalent ions which can condense DNA. And finally, I will show you for common divalent compound how to induce DNA attraction and how to regulate. Okay. So we use the magnetic tweezer, and I'll use dynamic light scattering, and for this one we use the single molecular electrophoresis by dyeing DNA molecule. Okay, so okay. So for people have known a long time, usually only more than 3 valence of a compound can condense DNA. However, only tetravalent compound can induce DNA charge inversion. So, what's the what's the reason? People argue that maybe the electric interaction or physical interaction play a key role. So it is due to the some kind of specific interaction like chemical binding. So here we show if it is because of electrostatic interaction. So if we change the dielectric environment, like we can change the dielectric constant. So if we decrease the dielectric constant, so the electrostatic interaction will enhance. So if we increase the dielectric constant, the electrostatic interaction become weaker. So here we try to add ethanol to lower the dielectric constant of solution, and see if it can induce the DNA charge inversion. So we do the experiment by electrophoretic light scattering. So it is the case. So for example, you can see here, So this is the K3, means we use the polylysine. So K3 is 3 polylysine, and the K4 means 4 peptide. And you can see here if there's no the black one. So if so is the normal solution. So it can so there's no charge inversion. So it can approach 0, but there's no charge inversion. However, if we add the ethanol, so here is 30% to 90%. So we indeed observed the charge inversion. So K4, it is able to induce charge inversion. However, if we add the ethanol into the solution, so the electrostatic interaction becomes stronger, so the charging inversion is promoted. So if we try to test if it is universal, so we use different counter ions, but with the same valence. So we use spermidine and spermine. This is 4. The valence is 4, and this valence is 3. So we observe the similar phenomena. So basically, so here we show that the electrostatic interaction is the main driving force for the DNA charge inversion. So in another way, if we this is similar, but we measure by the singular molecular electrophoresis. However, so in opposite way, if we increase the dielectric constant by adding tweezer ions into the medium or into the solution, so we indeed observe the in the opposite direction. So for example, here, okay, so for example, here we still use K4, but we add glycine and 6,8. This is another tweezer ions, but stronger. So here we can see K4 can cause DNA charge inversion. So here, but when we add glycine, so we can pull it back to the normal state, and at 6A, it's stronger. It's called amino caproic acid. So the same thing happens for K3 and spermidine and spermine. So here we show we can moderate the electrophoretic mobility of DNA into positive direction or negative direction. I mean, in 2 ways. Okay, and then we use magnetic tweezer to pull the DNA complex and to measure the condensing force, and we can observe the change of its condensing force, and the result is quite similar. Usually, when the DNA is most neutralized, the condensing force is maximized. Okay, so usually, so when the charge of DNA is most neutralized, so it means it's almost neutral. and we can observe the maximized condensed force. So from this observation, we conclude so maybe the electron interaction plays the key role to DNA charge inversion. So from this experiment, we support the idea, say, the charge inversion of DNA is purely electrostatic phenomena driven by maybe, so this is a popular theory called a strong correlation liquid of the contions. So, however, if we to test this, and we switch to more contions to test it. So we try some different contions. Here we use the ions iron, and so usually people think ions has some specific interaction with the phosphate. So in this case, the things is different. So we here, so this is the electrophoretic mobility of DNA. So here, the black line is so-called classical contions, and this is the what? This is the LA. So we use two different hydrolyzed contions, ions and aluminum, and we can observe it's the curve of charge electromobility is quite different. It's very sharp, and it looks like a all-in-one transition curve, and this is it's quite different from this, and this is the size of DNA, and shows a similar effect. So we wonder what happened, and here the ion shows it. Although they has three valence, but it can it can cause DNA charge inversion here. So we use atomic force microscopy, and show and we can see a all-in-one transition. There's no intermediate state can be observed. So we proposed a model here. So for some contions like ions, so it is interaction with DNA phosphate in a specific binding, but usually contions it interaction with DNA with Coulombic interaction, or the usual electrostatic interaction. And so the DNA, the interaction between so the charge the charge inversion of DNA can cause by different interaction. So actually, we try some organic monovalent ions. We use this tetral phenyl chloride arsenic. So we use this is because it can cause the latex charge inversion. So we use this to test DNA. And it found that although it is only, its valence is only 1, but it indeed causes DNA condense and can charge its, can invert DNA's charge. So here is the observation of atomic force microscopy, and we can see the DNA condense from here to here. And we also measure the condensing force by magnetic tweezer. So the condensing force increased with the concentration of the monovalent compounds. Yes, so it can cause DNA charge inversion here from here. See. So what is the cause to? Because the organic emollient is hydrophobic, so we infer the hydrophobic effect is the main driving force of DNA inversion here. So previously, a lot of speakers mentioned that maybe pH play some important role in DNA condensation and the charge regulation. It is. We just tested this by usual divalent compounds like magnesium and calcium, and it is. So firstly, we just use the AFM to observe the DNA morphology at a different pH. So from here to here, this is magnesium and this is calcium. So if we lower the pH of solution from like 7 to 3, we indeed observe the condensation of DNA. And then we pull the DNA by here. So when we lower the pH of solution in about 4, so we can observe the like intermediate state. So like here, so we can observe it can jump down and up here. So if we try to test it further by pulling the DNA and then switch the pH of solution alternately. So this is the cycle of by switch the pH of solution alternately. So here this is I think pH 3, and then we switch DNA switch the solution pH of solution into 8 here, and switch back and release, and then back. So it always can make many recycle. So so here, so the pH of media may play quite important role in DNA condensation or DNA compaction or DNA charge inversion. So let me summarize my talk as follows. So DNA compaction and charge neutralization can be a physical interaction like electrostatic interaction or some kind of specific binding like covalent like binding or some kind of hydrophobic interaction. And pH and ionic environment play a very important role in this process. Okay, thanks funding and my collaborators. Thank you.
Thank you. Questions?
You showed data using iron and aluminum triplus, right, in solution. And then you compared it with lanthanum, other trivalent ions.
Yes.
This is a difficult exercise. I'm not an inorganic chemist, but if you dissolve iron 3+, you get, depending on the pH, highly complicated structures. The worst for aluminum. So only if you go to very low pH values, you have maybe single ions. If you go to normal pH values, maybe around 7, and so on, you have a totally different structure, which you cannot compare at all with trivalent ions or well-behaved ions like lanthanum.
You're right, and we tried to use the ordinary compounds like La and like cohex, and then change the pH. But we can see the same effect like iron.
Because iron gives you, it is a polymeric structure. It's a big chunk of something swimming in solution, so it's not an ion anymore.
Okay, yeah. Okay.
Yeah, you had a summary slide for the first part.
Yes.
I think I just missed something, but I still want to check it. Earlier.
Yeah, I know.
Yeah. Okay. Yeah, I think I just wasn't paying attention. SCl, so that's a strongly correlated liquid. Did you develop on this? I didn't hear you.
Oh, no. This is the theory about the charging.
Yeah, I know what it is, but I'm not sure you said it.
Yeah, I just, well, actually, I support the first part, the charge inversion of DNA is, it seems from this experiment, seems it's caused by electrostatic interaction. But I don't know if it is indeed the charge correlation. But
to me, the first and the third at final temperature is the same.
Okay.
It's strongly correlated. Legal lattice only exists strictly at approaching zero temperature.
Oh, okay.
But at final temperature, it's basically high correlation effects, and that's what's happening in the first point.
Yeah, you're right. Thank you.
Yeah, I have a question about, you show AFM images of condensation by divalent ions at different pH.
Right.
Yeah. Okay, can you show me this slide?
Sure.
Yeah, so I wanted to ask you, Now the other one, the images. Now the AFM images.
Okay, AFM picture.
Yeah, that one, yes. I wanted to ask you, did you do this in the presence of ethanol or not?
No ethanol.
And how did you do the experiment? Did you prepare samples and then you spotted it?
Yes.
Yeah? Mm-hmm. Did you use ethanol for drying the specimens?
No.
So how did you dry them?
We just blow by nitrogen gas.
Okay. Now, I'm surprised that you find condensation by divalent ions, because for me that is a first.
Okay, thank you. Yeah, we
So if I can comment here, of all the divalents, I think only manganese at like 50 degrees condenses DNA in the bulk. Yeah, but the other ones don't.
So we try different like magnesium and calcium, and we got the same result.
Interesting. Yes.
You mentioned the size. Do you mean the size from the AFM or what you mean? Because
okay, yeah. We measure the size by a dynamic light scattering.
okay.
Mm-hmm. Thank you.
Okay, another question?
I understand how you can accommodate an excess charge if you are using a polycation. Usually the structure expands and you have all these arms hanging out of the complex. But I don't really see how you can accommodate excess charge with small ions.
We just measure the electrophoretic mobility of DNA.
Okay? It's a result.
Yeah.
Any more questions? I guess we are all getting tired and maybe hungry. So thank you, and thanks to all the speakers.